Hello and welcome to this video lecture. In this lecture, we're going to talk about the integration factor. And so we'll see that the integration factor is a very clever means to help us solve some what I would consider slightly more difficult first order ordinary differential equations. So let's go ahead, and again, this is in the vein of us at least initially talking about first order differential equations, so we're still talking about those at this point. So for a first order linear ordinary differential equation, ODE, but this time we will allow, well, let me spell out with. So I may refer to with as W with a slash, but here I'll actually spell it out and then introduce it as W with a slash. So with variable coefficients this time. So before we were talking about LTI systems, linear time invariant, where the coefficients didn't change in time, representing that we had a constant system configuration, not necessarily constant response, but at least the system configuration was constant, i.e. The system wasn't changing in mass or other things weren't changing potentially in time. Now we're actually allowing for variable coefficients. And so that means that we can actually account for things where maybe the mass is changing in time in the system or something along those lines. Now, of course, we'll discuss it just from a abstract perspective based solely in math, though here through the discussion, hopefully you can see that we could do different things with this, at least from a mechanical engineering perspective if we wanted to. So let's go ahead and say that we have a form for this differential equation, C1t times dx dt plus C naught. Don't know why my pen's kind of writing funny again. Plus C naught of t times x. And this is equal to g of t. So here we can see that the leading coefficient is a function of time. We really don't need to have that function of time. So let's go ahead then and divide through by C1 of t so that we end up with a coefficient of unity for our term that has the derivative. So then we have dx dt plus, here I'll just call it C of t times x is equal to now f of t, where we have a couple things going on. Let me put my h in there first. Nope, sorry folks. For some reason it decided to change scaling there on me. Let me see if I can rescale it so that we're back to something more normal. There we go. And for some reason the pen doesn't seem to want to come up. Okay, there we go. Okay, and so you can see that we've substituted a couple things in. We have, let me just write a little further over. We have C of t, of course, is now equal to C naught of t over C1 of t. And we have f of t is equal to g of t, again, over that same C1 of t. Those, of course, are going to be functions of time, even though they may be somewhat complex functions of time. So now let's go ahead and here's where things get really interesting. Let's let this C of t equal a particular form. And we're just going to find the functions we need to find to make sure that this form works out. So we're going to force this C of t, essentially, if you want to look at it that way, we're going to force C of t into this form, 1 over P of t times dP of t dt. So we're going to say that whatever C of t is, we're going to force it into this form where 1 over a function P of t times the derivative of that same function P of t will allow us to recover C of t. Now, you might think, well, why are we doing this? Well, it turns out that this is, as I indicated, a very clever approach to solving this differential equation, this class of differential equations. Because what it does is it takes a differential equation that would be very difficult for us to solve potentially, and it cleaves the problem into two very manageable subproblems. So the overall problem is very difficult, but this particular approach, just forcing C of t into this form, allows us to break the problem in half into two I wouldn't say very simple, but two relatively simple problems that are definitely very doable. So let's go ahead and see how that works. So we're allowing, or we're forcing, might be a better way to say it, we're forcing C of t into this form. So then, substituting C of t back into the original differential equation, we get dx of t. And I hope you really enjoy this because I think this is truly phenomenal. So we get dx dt plus 1 over P of t times dP of t dt times x is equal to f of t. So now we can go ahead and multiply through by P of t. So we have this 1 over P of t. Let's just multiply everything through by P of t. And when we do that, we then get P of t times dx dt plus dP of t dt times x is equal to P of t times f of t. And maybe you're starting to see how ingenious this is, specifically on the left-hand side, because that is a pretty nifty form, one that you might be recognizing. It may take you a moment, but don't worry. Let's go ahead. So if you want, pause it now, look at it, see if you can figure it out. But if you don't want to, or you already have paused it and figured it out, let's go ahead and spill the beans now. So because we forced C of t into this form, look at what we have on that left-hand side. We have the product rule for a derivative, or for differentiation would be a better way to say it. And that is pretty darn cool. So let's go ahead, because of course that means we can work with that pretty effectively, because we can then say, that means that we're really finding the derivative on the left-hand side. We're finding the derivative, not two different derivatives and multiplying them in two different terms. We really only have a single derivative and a single term, which is the product of p of t times x. So we have d dt of p times x. And of course, if you went ahead and just to show it to you, and we worked with the product rule, we clearly get dp of t dt times x plus p of t times dx dt, which is exactly the same thing as this left-hand side, just the terms are, of course, reversed in order, reversed in order. That's all I should say. Okay, so great. That means then that we can rewrite, sorry, got my parenthesis off there a little bit. We can rewrite that differential equation, obviously, then as d dt of p of t times x is equal to p of t times f of t. And so going ahead and integrating both sides, we get rid of the d dt, and then taking p of t over to the other side, we solve for x, which is what we want to find. So there we go, we have our solution. So, and x, let me kind of go down into a half line if that's okay with you all. And x is equal to 1 over p of t times the integral of p of t times f of t dt. So we just go ahead, take these functions of time, they're known. We take these functions of time, we multiply those two functions of time together and integrate them relative to time. Whatever we get, we divide by p of t, and there we go. We have x, which solves this function of x, specifically x as a function of time, that solves our differential equation. So that's pretty darn cool. So there we go. We made the substitution, and the solution half became incredibly simple. The one thing we assume, though, is that we know p of t. At this point, we don't know what p of t is, because remember, we're forcing c of t into this form that is related to p of t. But that's okay. Let's go back up to that, and let's see if we can figure out a way to come up with an expression for p of t. And if we can, then we're done. We have the solution half, and then we have the other half that allows us to find the function to then go and find the solution. So let's go ahead and see if we can work that other half. Now, of course, since I'm presenting this in this class, it means that, yes, surely enough, somebody figured it out. So then what's p of t? So going back, as I said, from c of t, so again, this is now the other sub-problem that we need to work, is finding that p of t. So from c of t, we have 1 over p of t times dp of t dt. Now let's go ahead and multiply both sides by dt. Let's just put it up here. And then that leads us to dp of t over p of t is equal to c of t dt. Well, that is a particularly nice expression to integrate. So let's go ahead and integrate both sides now. And when we do that, what we can see is that clearly we have the derivative of the function over the function itself on the left-hand side. Well, what's that going to be? That's just simply the natural log. So we get the natural log of p of t. Here we will have a constant of integration 2, because of course I'm just dealing with the indefinite integral. And that's equal to the integral of c of t dt. Now, to make things a little bit easier, let's go ahead and integrate from 0 to t, where we're still capturing the fact that we have this parameter t that we're going to end up with in this expression, c of t times dt, but we'll explicitly pull out the constant of integration, k2. And the reason I'll do this is because it makes our lives a little bit easier dealing with the constants kind of together right now rather than separately. Because if we hold on to them and do the integration or work with the constant of integration later, it becomes a little bit uglier. Not terribly bad, but a little bit. So we go ahead and we're still capturing t here, no problem. And we have our constant of integration. So of course, what does that mean? That means that I can take my K1 and I can take it over to this other side and combine it with K2. So I'm going to do that and I'm going to call that K3. So note K3 will be equal to K2 minus K1. So just a little note there. And so let's go ahead then and solve for P of t, because remember, that's what we're trying to find, and having it here embedded in this ln isn't going to do it for us. So then we have P of t is equal to, so I took K1 over, so then I can take the exponential function of both sides, the inverse of the natural log. So then I just recover P of t, but then that means that the entire right-hand side is raised to the exponential function. Now notice that this integral is in the argument of the exponential function. So it might look a little bit funky, but really doesn't matter. So no, it doesn't. All it means is you just integrate the argument before you write it into the exponential function. That's all it says. And then we have K3. Now, one of the wonderful properties of the exponential function is when we're adding things together in the argument, we can instead go ahead and write the arguments separately raised to their own exponential function. That's one of the properties of the exponential function. So that's a pretty nice property. But let me ask you, E is what? E is a constant. K3 is what? K3 is a constant. Taking a constant and raising it to another constant gives me what? A constant. So we can then say, and this is what I like to call, and I hope you have fun with it like I do in this class, but we run into this all the time. This is what I like to call our constant nightmare, because, yeah, never mind, you get it. Okay, so anyway, with that, we have P of t is equal to let me get my constant in first, right? Because we're just going to turn that exponential function raised to a constant into just another constant. So we'll just call it K, because this is something we're used to seeing. E to the integral of 0 to t of C of t dt. And that's beautiful, because pretty much all I have to do to find my P of t is I just have to integrate C of t, which we got from the original, after modifying the original differential equation a little bit. We just integrate that C of t, and we just plunk it in to the argument, or plug it in as the argument of the exponential function, multiply it by this K, and we're good to go. We have our P of t. And then what do? We run with that P of t right back up here, and we find our X. That's it. And so neither of these two halves are terribly difficult, assuming that the functions are integrable. Uh, they're not really that difficult. And so you can see how we went from a problem where we would just be kind of literally guessing a solution if we ever got there at all, now to a problem where, okay, I do this one step, I solve this one subproblem, namely the first subproblem you solve is finding P of t, and then the second subproblem you solve, and really not even a problem, the second thing you do. So the first thing you do is you plug into this equation for P of t, and the second thing you do is you plug into this equation for x, the solution. That's it. So I shouldn't even say that it's two subproblems, it's just two things that you do. So very, very simple. And that's why this method is so powerful, because it allows us to, using these relatively simple expressions, they're deserving of boxes, I think. Let's go ahead and box these up. So using these two relatively simple expressions, we can find a solution, or we can find the solution for what would generally be considered a very difficult differential equation to solve. So let's go ahead and work an example. Let's say that we want to find the system response and let's say that we're given dx dt plus 4t plus 3 times x is equal to e to the negative 2t squared. So you can see that this is a linear differential equation, non-homogeneous, of course. So this is a linear, non-homogeneous. First order, let's better get that down too. Ordinary differential equation, didn't really need that last comma there, my apologies. And so that's perfect for what we're trying to do. So let's first find, and so didn't really introduce it in lecture, but let's go ahead and introduce it now. So clearly that function P of t is a pretty important function. And so as is the namesake of this lecture, that function is what's called the integration factor. So the integration factor, P of t in this particular case, so remember that's what I said is we have two kind of sub-steps. We find P of t first, and then we find our x, specifically x of t. So P of t is equal to k e, so just writing it down generally, integral from 0 to t of c of t dt. But for us, that's equal to k e to the integral 0 to t of 4t plus 3 dt, which is, of course, a really simple polynomial to work with. And so you can see that we're going to have k, e, and the limits of integration for a polynomial, obviously. Now, remember, we don't include the constant of integration. That's one of the other things that I do want to mention. Do not include the constant of integration when you do this integral. You shouldn't, because we have limits of integration. But I want to make sure that you understand that. So, of course, when we have a polynomial and you substitute in 0, what are you going to get? You're going to get 0. When you plug in t, you're just going to recover t. And so what we get from this particular one is we obviously get 2t squared plus 3t. Okay? Now, technically, we have plus 0 when we substitute in 0 there, but I'm not going to worry too much about that. So now that we have our integration factor, let's do P of t again, just even though it is a continuation, I just want to make it extremely clear that we have that P of t going on there. So then we need to solve for x. Well, you just substitute in for x, that's it. Or you just drop these functions in for x. So we get 1 over k e to the 2t squared plus 3t. And then we have the integral of p of t times f of t, where f of t was given as negative 2t squared. Well, that was a convenient choice of functions. Yes, I know it was. Thank you. So anyway, and then of course we need our dt. So let's go ahead and plop that in there. And so then one thing that we can clearly see is we have a k here, constant. We can factor that out. We have a k over here in the denominator, same constant. We can cancel those out. And then, of course, we can take this 1 over e, and we can turn that into e to the negative 2t squared plus 3t. And then we just have the integral. And just like we were able to break apart the argument of the exponential function when they were added together into two exponential functions multiplied together, we can do just the opposite. If we have two exponential functions multiplied together, we can just add their arguments together. So then we get e to the 2t squared plus 3t minus 2t squared, right? That's why I just complimented myself, times dt. And of course, those cancel on out. And then we're just simply left with e to the negative 2t squared plus 3t times the integral e to the 3t dt. And so now we can do a u substitution if we like. This is obviously a relatively simple integral at this point, but let me work through it with the u substitution. So u is equal to 3t because it just makes things a little bit easier to make sure we don't make mistakes. Then obviously du is equal to 3 dt. And last but not least, dt is equal to 1/3 du. So now substituting all that in, we simply get that this is equal to, I'm not going to do the u's out in front here though, because I'll back substitute in for the t's. So we just keep this leading function of t here, and then we get an integral of e to the u times 1/3 du. So that's how we can see the 1/3 comes out. It just makes it a little bit easier to see that. And so then integrating e to the u du, factoring out that 1/3, integrating e to the u du, we get e to the u. And then we can back substitute in this 3t for e to the u, or into e to the u. So going ahead, we get e to the negative 2t squared plus 3t times e to the 3t times 1/3. One thing, let me make sure I get that in there though. We do need our constant of integration k. Here, let's call it k1, because that is an indefinite integral, and I haven't yet explicitly taken care of the constant of integration. So for this integral, obviously we have to capture that there is a constant of integration. So please make sure that you do that whenever you're working through these kinds of problems. So then last but not least, and again here I'm just going to get an exponential function times another exponential function, so I can go ahead and combine those together. And so I get a 1/3 e to the negative 2t squared minus 3t. And then from this one, I'm going to get a plus 3t. And so, of course, those are going to cancel out. And then I'm going to have a plus k1 times e to that, and then nothing's going to simplify over here. So I just rewrite this particular function, and there we go. And so last but not least, we find that x is equal to not 1/2, 1/3. Come on, 1/3, there we go. E to the negative 2t squared plus k1 times e to the negative 2t squared plus 3t. And let's go ahead and box that on up. There we go. Now, as I've indicated before, probably a number of times by now, let's go ahead and check our answer. So to check this answer, we simply take the derivative, dx dt, because we already have x, right? So we just substitute that back in, but I also need the derivative, so dx dt. So here we get a 1/3, and then of course we have the derivative of the argument to the exponential function that comes down as well. So we get a negative 4 times t, because the t squared becomes 2t when we take the derivative. And then we have e to the negative 2t squared plus, then we have our k1, and then we do the same thing over here with this exponential function. So we take the derivative of this argument and bring that out on front, or back out in front, and so then we get a negative 4t plus 3 times e to the very same argument again, 2t squared plus 3t. And then we close that on down. And now we substitute back into our original differential equation, which, just to remind you so we don't have to go all the way back up to the top, is d dt plus 4t plus 3 x is equal to e to the negative 2t. So let's see if that all checks out. So substituting our derivative in, we get, I guess I'll start over here, 1/3. Actually, let's just do our negative 4/3. Negative 4/3 t times e to the negative 2t squared plus then, I guess we don't need that plus sign. We have a minus that we're getting from inside. So we have this minus here. So I can just go ahead and bring that on out. So minus k1 4t plus 3 e to the negative 2t squared plus 3t. And then we have our plus, so that took care of the derivative. So now we have plus all of this times x. Well, remember this is x right up here. So I can just distribute that across this x, this quantity associated with x. So let's do that. So we get a 1/3 times 4t plus 3 now times e to the negative 2t squared plus k1 times that very same 4t plus 3, all that times e to the negative 2t squared plus 3t, and that needs to be equal to e to the negative 2t. Well, that's kind of nice, isn't it? Because look at what happens. This guy is the same as this guy, except opposite signs, plus, minus. Yay! Cancel. Cancel. And if you haven't figured it out yet as mechanical engineers, your favoriteest thing as a mechanical engineer by now should be what? Canceling things. Didn't you know that that's the entire reason you became a mechanical engineer, was to be able to cancel this stuff out? So anyway, with that said, what do we have going on now? Well, we have a negative, so we still need to distribute this guy on out a little bit more. So let's go ahead and do that. So we have a negative 4/3 t, e to the negative 2t squared. Going ahead and distributing everything on out here, we get a positive 4/3 t times e to the negative 2t squared plus a 1/3 times 3. Well, that's just going to give me a 1. So that's going to be e to the negative 2t squared. And we're hoping that that's equal to negative 2t squared. Let me see. Did I accidentally did let me make sure I got everything right here. Oh, I miswrote myself. My apologies. So I miscopied this. That's a t squared. Whew. Okay, things are looking better. Thank goodness. So this is a t squared. So please add in those squareds. My mistake for having missed that. My apologies. And so then we need to make sure that this is equal to 2t squared. I got it right in my notes, just missed it here. And so, of course, we can see exactly what's going on. Clearly, those are the same quantities, just opposite signs, so they cancel. And of course, we're left with e to the negative 2t squared is equal to e to the negative 2t squared. Sure enough, that is our solution to this differential equation. And so we're good to go. So hopefully this particular video lecture has given you a chance to see that even with a complicated first order linear ODE, but with non-constant coefficients, that's a pretty tough problem to solve. Even with that, again, provided all the functions are able to be integrated, we're able to break that difficult problem apart into two relatively simple relationships that we just need to solve individually, though of course one folds into the other, and then we get a solution. We can find our solution. So hopefully you can see how powerful this approach is. It's incredibly interesting how that one, just taking that function of time and forcing it into a particular form can give us such a powerful result. So with that, I'll call this video lecture a wrap.